You know, when you see a modern prosthesis, it's easy to think of it as just one single high-tech product. But that's not the whole story. It's actually more like a personal puzzle, a unique solution that's built piece by piece. Not for just anyone, but for one specific person. So today, we're going to look at how that puzzle gets solved.
Okay, just look at this thing. It is an absolutely incredible piece of engineering. But what you're seeing isn't just one device. It's actually a whole system of different components, and every single one is chosen and assembled to meet one person's specific needs and goals. So we're going to break down exactly how that happens, piece by piece.
And right from the get-go, our source material makes one thing totally clear. The most important person on this design team, it's not the engineer, it's not the doctor, it's the user. Their life, their ambitions, their feedback, that's what drives every single decision that comes next.
So here's our roadmap for today. We'll kick things off with the big picture goal. Then we'll dive into the key puzzle pieces, that all-important K level, the foot, the socket, and the knee joint. And then finally, we'll see how it all comes together in the end.
Right. So before a single component is even considered, the team has to agree on the ultimate goal. And it's so much bigger than just replacing a limb. It's really about restoring mobility, boosting independence, and, just enhancing a person's entire quality of life.
So, how in the world does a medical team take those big life goals and turn them into actual technical specs? Well, it all starts with one crucial measurement that basically guides every other decision in the process.
I mean, just think about it for a second. There are dozens of types of prosthetic feet, different knees, different sockets. You've got mechanical ones, hydraulic ones, microprocessor-controlled ones. It's this huge menu of options. So where do you even begin?
Well, the answer is something called the K level. You can think of it as the master blueprint for the entire prosthesis. It's this standardized scale that assesses a person's current activity level and also their potential for activity. And this one rating, it's a number from K0 to K4. It basically determines what kind of technology is medically appropriate.
And when you break it down, it's actually pretty intuitive. So a K1 level, that describes someone who's mainly going to be walking at home on flat surfaces. A K2 user can handle a few small obstacles like curbs. K3 is for someone who's active out in the community, walking at different speeds. And K4, well, that's for your highest activity users. Think athletes, very active adults, or even kids.
And this is the actual chart clinicians use to figure it all out. And it's not just some casual guideline, it lays out really specific criteria for each level. In a lot of places, this determination is what directly impacts which prosthetic parts get covered by insurance, so it brings a lot of much-needed objectivity to a really complex decision.
Okay, so once that K-level blueprint is set, the team can start putting the prosthesis together, and they do it literally from the ground up. The very first choice is the foot. And this is a perfect example of that direct link between K-level and technology. Over on the left, you've got a simple, super durable Sachs foot. It's perfect for a K1 user. But on the right, that's a lightweight, energy-storing carbon fiber foot, designed to give a spring in the step for a much more active K3 or K4 user. Two totally different designs for two totally different lives.
And the options go way beyond just those two. The technology really scales up with the activity level. A single-access foot gives you some basic ankle motion, good for K1 or K2. A multi-axial foot can handle uneven ground. Then you get into things like hydraulic feet, which help you walk more naturally on ramps. And at the very top, you've got microprocessor feet that are actively adjusting to different surfaces, even the height of your shoes, in real time.
All right, moving up the leg, we get to what many people would say is the most critical and definitely the most personalized part of the entire system, the socket. The socket is the direct connection between the human and the technology. I mean, you could have the most advanced foot or knee in the world, but it's all useless if the socket doesn't fit perfectly. The best way to think about it is like a shoe that's the wrong size. If it's off, it's going to cause pain, it's going to be unstable, and the whole system just fails. It has to be custom molded to spread weight evenly and translate the user's own movements into action.
And here, you can really see how all those puzzle pieces snap together. You've got the foot at the bottom, that custom-molded socket at the top, and in between them is the pylon. That's the structural pipe connecting them. It all works together as this single integrated system where, really, the success of the whole thing depends on the perfection of each part.
So of course, the socket has to stay on securely, right? That's the job of the suspension system. And we have come a long way from old-fashioned straps.
Modern systems use things like pin locks, suction, or even active vacuum pumps to create this incredibly secure connection. And this isn't just about keeping the leg from falling off. A better suspension means better control, you waste less energy, and you have way more confidence with every single step.
Now, for an above-knee prosthesis, there's one more major component, and it's usually the most technologically complex one of all, the knee joint. This is basically the engine of the whole system.
At a really basic level, knees are defined by their axes. A monocentric knee, that's single axis, is simple and lightweight, but a polycentric knee, which rotates on multiple axes, does a much better job of mimicking the way a human knee actually moves, and that provides a lot more stability.
But where things get really fascinating is in the control system. The technology progresses in these really clear steps, so simple mechanical knees use basic friction to work. Pneumatic knees use air pressure to control the swing of the leg. Hydraulic knees use fluid, which gives you even smoother control, especially on things like ramps or stairs. And then at the very top, you have microprocessor knees, with tiny onboard computers and sensors that are analyzing a person's walk hundreds of times a second to adapt on the fly.
And you might be wondering, okay, that sounds fancy, but what's the real-world difference? Well, it's huge. The research shows that microprocessor knees don't just feel better, they are scientifically proven to significantly reduce stumbles and falls. For a user, that's the difference between walking down a hill with confidence versus constantly worrying about your next step. It's a massive game changer for safety and mobility. The main trade-off, of course, like with most cutting-edge tech, is the higher cost.
So, after looking at the K level, the foot, the socket, and the knee, let's pull it all together and look at the final picture.
And really, this is the key takeaway of this whole thing. There is no such thing as the best prosthesis. It just doesn't exist. There's only the best prosthesis for you. It's this unique combination of all these parts, carefully chosen and custom built to match one person's body, one person's activity level, and one person's goals. It's the solution to a deeply personal puzzle.
Which kind of leaves us with one final big question. We now have technology that can actively prevent falls, that can adapt to the world around it in real time. That is an incredible achievement. So, what's the next frontier? Is it better energy efficiency? Is it direct connection to the nervous system? Or is it something else we haven't even thought of yet? The puzzle, it seems, is never truly finished.